So today we're going to talk about PET, PCT, and all of their derivatives. PET is an incredible material. It's near ubiquitous. You see it all the time. It's what soda bottles are made out of, for example. It's a really incredible material that's commonly used in injection molding, right? It's used all the time because it has great mechanical properties. First of all, it's extremely cheap. Second, it can be manufactured to be very optically clear and have like good optical qualities. It's strong, it's chemical resistant, and it's relatively easy to work with, right? So PET is used all over the place, and it has a sister chemical. That sister chemical is PCT. It's extremely similar. It's basically the exact same stuff. But the biggest difference is that PCT is supposedly a little bit better in like every quality metric that PET is measured in. Perhaps most notably, it's better, it's more chemically resistant than PET is. And so if you have a very specific use case where you need that additional chemical resistance, then PCT is your choice. And it's kind of a no-brainer. But the relative costs between PET and PCT are enough that under pretty much any other circumstance, it almost doesn't make any sense to choose PCT over PET. PET is very, very cheap. PCT is a little bit more expensive. Its derivatives are a lot more expensive when it comes to 3D printing materials. And so my personal experience and recommendation is that PCT derivatives just aren't worth it. But we'll get into that in just a little bit. Now, the thing about PET manufacturing is that when they injection mold a part, like, for example, a soda bottle, what they do is they take a slag of molten PET and they put it on the end of a hose. And they take that hose with the PET slag on the end and they put it into a mold. And then they use essentially like a high pressure system to blow that PET into the shape of the mold. It then takes the form of the part that they're trying to create, and then they cool it. And when they cool it, the PET changes from an amorphous arrangement of molecules into a crystalline form. This rearrangement of the molecules causes the PET to reduce in volume, right? So it will shrink a little bit compared to its amorphous form. Now, in an injection molding scenario, that's not a very big deal because we continue to apply pressure into the mold and the mold applies pressure back. And so the molded part has nowhere to go. It has to essentially shrink into its current shape. But that's not true with 3D printing. When you have a 3D printing filament like PET, and as you print it, it reduces in size as it cools, which it must do in order for it to convert from a liquid to a solid, it's going to warp, right? And it's going to warp quite a lot. In fact, PET is one of the materials that is most likely to warp the most of all 3D printing materials. So this is a really big problem, and maybe someday people will figure out how to perform controlled warping where their models are intentionally distorted in such a way that as they warp into the intended shape. But right now, no one's really kind of got that working well, and it would require some very fine degrees of control around cooling, and the environment would have to be controlled in a very specific way. So it might not be realistic in the near-term future to intentionally deform PET prints that way.
So while I was editing this video, and look, it takes a long time for me to edit things because this is just not my job. It's something that I'm doing, kind of lackadaisically, and I know that I should do better and I should do things faster, but I just have other priorities, and so I can't move on this as quickly as I think some other creators probably can. But anyway, while I was filming this, or while I was editing it anyway, Bamboo Labs came out with a new feature, or I guess a new partnership, with a company called Helios. Helio, which does some sort of thermodynamics simulation. And it's clear what direction they're going in. They're actually going to try to solve this problem that I am talking about in this video. So right now, all it does, I was one of the lucky people to get one of the beta invites to use this, and I have tried it a couple of times. All it does is this. It shows essentially what the thermal impact is and how cooling will occur on your part as it's printing. And based on what it's showing in this simulation, I don't know if I totally believe it. I think it probably has a little bit of room for improvement just on that. It only supports a handful of different materials. Those materials are mostly the materials that are least affected by cooling that cause warping the least, like PLA, for example. They've got a bunch of different kinds of PLA. I'm really not worried about warping with PLA. But it's clear where they're going with this, right? It seems to me like ultimately what they're trying to do is come up with profiles of anticipated warpage based on the way that a particular material is cooling. And that might eventually give us this predictability in how certain high warp materials like PET may warp as they are printed. And knowing that, you could potentially have that algorithm imply, somehow determine how to preemptively warp your models in a way that they will warp into the intended shape. But again, as I've said previously, this might be very, very complicated, and it's probably several years away at the absolute soonest. And so I don't, even if someone comes out with an application that actually does this, even if somehow Helio simulation actually becomes really good at doing that, I don't expect that it's going to have the anti-warping, intentional pre-warping capability, or if it does have it, it will not be accurate at all for several years. But it's a really interesting development, and we're headed in the right direction here. Okay, back to the video.
And so, because of that, working with PET itself is not easy to do. We typically don't do a lot of 3D printing with this material, even though it's quite a good material. Now, to solve this problem of shrinkage, there's a couple of different things that the manufacturers in the industry of filament have done that do make a really big difference in how much warpage we typically see in PET prints. The first thing that they do, that they commonly will do, is add fibers to the filament, which act as a scaffolding and kind of a rebar in the filament that prevent that filament from shrinking too much, right? So what we are talking about here is, let's say, glass fibers, right? Very common material. The glass fibers are scattered randomly throughout the filament. They're very, very tiny. We're talking about almost a finely ground dust of glass fibers that are kind of sprinkled into the PET mixture. But if you look at them under a microscope, what you'll see is like relatively sharp shards of glass that are longer than they are wide, right? And that material being distributed through the filament gives the PET something to hold on to. And so you'll have these like hardened fibers that are kind of randomly arranged throughout the filament. And as the filament tries to shrink, it's holding on to those glass fibers, and the glass fibers don't allow it to shrink quite as much. Now, the spaces between the glass fibers, that part can shrink still, and so it will still shrink somewhat, but not as much as it would without the glass fibers. So it makes a pretty big difference. Now, glass fibers are also pretty neat because they will add some rigidity to your print, right? The glass itself adds a little bit of strength and a little bit of hardness to your 3D prints, and adds potentially a little bit of tensile strength as well. But it comes at a cost. The cost is, first of all, actual cost, financial cost. It certainly adds some price to the material that you're buying and can make it quite expensive in some cases. But it also comes at the cost of layer adhesion. So when we're 3D printing a filament that doesn't have a fiber in it, we have a clean layer of plastic laid on top of another clean layer of plastic. And the interface between those two layers, where the plastic touches, is pretty much continuous. It's as much surface area as it possibly could be. But if you think about having a bunch of fibers, like glass fibers, sticking out of that filament all over the place, right? So there's going to be like pointed, jagged glass fiber sticking out all over from each layer. First, the layer that is coming from underneath and the layer going on top. The effect is small. It's small enough that you'd have to look at it under a microscope to see it, but there's kind of a tenting effect where the plastic is resting on top of a glass shard, causing it to not make complete contact with the plastic around it, right? And so you're going to have this effect thousands or millions of times and reduce the total surface contact patch between those two layers by some amount, by some percentage. And that amount that the contact patch has been reduced is likely to weaken the layer strength, the layer adhesion strength of your 3D print by some corresponding amount, right? It's not an exact science, but it's going to have some effect that will certainly reduce the strength of your layer adhesion. Now, glass fibers are pretty cool, and they do a really good job, and that cost might be one that we're willing to accept, especially considering that those glass fibers are clear, and so they don't have a major effect on the pigmentation of the filament that they're in. So you can get glass fiber filaments in really stunning colors, including even white, right? Which is quite different from the other fibrous material that we usually use in 3D printing materials, like carbon fiber. This is PET with carbon fiber in it. Now this stuff is made by QIDI Tech, QIDI Tech. I presume that that's how you pronounce that. And this stuff is really incredible. It's pretty remarkable. Now, the thing is that our expectations are that layer adhesion is going to be dramatically reduced by having carbon fibers in your filament. My tech fund did some testing with this, and if you believe his results, which I do, you'll see that this actually outperforms pretty much any PET from a layer bonding perspective. And it's stronger in pretty much every single way. So I don't know how they did that voodoo, but they somehow did. And so I really, really love this material. It's incredibly strong, it's very expensive, and it only ever comes in black. Let's talk about what carbon fibers are and how they're different from glass fibers. So when we say carbon fiber, and I apologize for most of the people who already know this stuff, I think that most beginners get a little bit confused. Most people hear that we're printing with carbon fiber, 3D printing carbon fiber, and they're imagining that you could 3D print a Ferrari's fender or something like that, right? That's not what we're talking about. It's really not what we're talking about. So carbon fiber starts off as a chemical called PAN. And that PAN is spun into very tiny threads, right? PAN is a molecule that is it's very rich in carbon, right? So they make these very tiny threads, lots and lots of them, thousands or millions of them. And then they cook those threads at a very, very high temperature, like 1,000 degrees Celsius. And when they do that, all of the atoms in that PAN thread that are not carbon leave. They basically burn away. And all that's left is carbon atoms. And when you have essentially a lot of very hot carbon atoms wobbling around that are kind of free, and you let them cool on their own in a very specific and controlled way, those carbon atoms will form into hexagons, a little bit like the hexagons on this crate. They form into hexagons, essentially a carbon atom at each vertex, right? And it's a two-dimensional sheet of these hexagons of carbon. And that is a material that is called graphene, right? Graphene's an astounding material. It's incredibly strong. It has really interesting properties, including bizarre electrical conductivity and also resistance properties and crazy stuff like that. It's really, really useful stuff. But when we take a thread of PAN and we burn off all the molecules and atoms that are not carbon, and we let it cool until it becomes sheets of graphene, those sheets of graphene are of random size and orientation. So they're like sheets that are kind of in a bunch of different directions, and they're all random sizes. Some of them are balled up, some of them have imperfections in them. They're not like stacked nicely, right? When you have a bunch of randomly sized sheets of graphene kind of stacked together in kind of a haphazard way, you have graphite, right? That's what graphite is. And in this case, we're talking about, relatively high quality graphite, but it is not anything like graphene. Now, those like layers of the graphene being stuck together like this and kind of stacked on top of each other are held together with forces like van der Waals forces and electrostatic forces and things like this, right? So they're kind of held together in the same way that cyanoacrylate glue holds two parts together, right? They fill in crevices and there's friction between them, and it's incredibly strong, right? This is an amazingly strong material, and it has a very high tensile strength as graphite. But it is exactly nothing like having pure graphene, right? If we had a huge sheet of pure graphene, it would be way stronger than what we're talking about when we're talking about graphite, right? Now, the fact that there are threads of graphite often confuses people into thinking that what they're looking at is carbon nanotubes. And it is definitely not a carbon nanotube. A carbon nanotube is a very specific and incredible thing. A carbon nanotube is when you take a sheet of graphene that's one atom thick and you roll it into a cylinder. And that is a wonder material, right? It's a miraculous material. It's thousands of times stronger than steel, but it is nearly impossible to manufacture. It's definitely very expensive and difficult to manufacture in quantity, and that's why today, kind of the state of the art of manufacturing carbon nanotubes is that we make them essentially one at a time, and usually not longer than about 3 feet at a time, right? And a 3-foot carbon nanotube is not something that you would be able to see with the naked eye. We're talking about trillions of times thinner than a human hair, right? This is not even remotely close to something that you could see. But if you were able to manufacture several carbon nanotubes, and by several I mean millions or billions or trillions or quadrillions of them, and bundle them together, braid them, whatever, weave them, spin them together, right, and make an actual thread out of carbon nanotubes, you would have a truly remarkable material. This is what they're talking about when they're talking about the space elevator that they want to build out of carbon nanotubes. That's how they want to do it, right? We have nowhere near the technology to build that many high quality carbon nanotubes. It's at the moment pure fantasy, but sometime in the future, if they can figure out how to do it in mass, this will be a new wonder material. And I'm telling you all this just to be clear that we're absolutely not talking about carbon nanotubes when we're talking about carbon fibers. Not the same thing. Okay, so when we're making a Ferrari fender out of carbon fibers, we now take the graphite threads and we make a fabric out of them. We make a fabric out of them by essentially, first of all, taking those threads and kind of making them coherent, and then we weave them together and we make like a weave pattern. That's why carbon fiber kind of has that checkerboard effect, right? Because it's woven together. When they make that fabric, it's kind of a fairly stiff fabric. It's not something that you could like make clothes out of, right? It's like it's too stiff and too difficult to like bend into shape. So what they do with it is they take the carbon fiber sheets and they kind of press them really hard into a mold, and then they coat that carbon fiber sheets with a layer of an epoxy resin. And that epoxy resin, first of all, makes the carbon fiber sheet malleable enough that it will fit into the mold quite well, A, and B, it holds multiple layers of those carbon fiber sheets together and then solidifies them in the shape of the mold, right? And then essentially when we remove the carbon fiber part from the mold, what we are left with is this composite material. It's carbon fiber sheets that are woven, held together by a very high quality epoxy resin. Now, the epoxy resin on its own is strong, but not very strong. And the carbon fiber on its own is strong, but not super strong, and also it's kind of floppy. But when you mix these two things together, what you get is an incredibly lightweight material that is impossibly strong for its weight. It's a pain in the ass to work with, and that's why it's not everywhere, right? That's why we find it on high-end stuff. But it is an incredible material. So, are we talking about that? Kinda. So if you go all the way back to the beginning of that process, where we have the PAN, and we have drawn it out into threads, and then we've cooked that PAN so that it becomes graphite. So we have these graphite threads. Instead of then weaving that together into a fabric, if we ground that material into essentially a very fine dust, that's the carbon fibers that we typically see with 3D printing materials. That's what we're talking about here, is very tiny chunks of carbon fibers that have been chopped up and then added to our material for the specific properties that they gain by having carbon fiber in them. Now, that has the effect, because the carbon fibers, this graphite, is like a very dark gray color, it does change the color of the material that it is being added to, and it becomes a darker color, a dark enough color, that most manufacturers simply just make all of their carbon fiber filaments black. But not all of them do. You can actually get some materials that are just like dark colored with carbon fiber in them, and we'll actually look at a couple in just a moment. Now, the carbon fiber has all the exact same benefits as the glass fibers do, except maybe taken just slightly to the next level. They have the same problems, which is that, you know, layer adhesion is certainly a problem. They're a lot more expensive, but they also have all the same benefits. They tend to cause parts to not warp as much as they would without the carbon fibers while they're being printed. It also makes the parts a lot more rigid, stiffer, and it actually kind of changes the finish of the part as well. It makes it look, I don't know, fuzzier. Maybe that's not the right word. It just looks more matte, right? It's a little bit less shiny. And it's actually quite a very good look. It looks really nice. And so it's a very popular additive that a lot of companies have put into their products. Now, this layer adhesion problem, a lot of companies have tried to solve this in some very interesting and innovative ways. And one of the ways that they tried to solve this problem is by creating fibrous core filaments. What they went for was essentially they would put all of the carbon fiber in the center of the filament, and then wrap the rest of the filament, the actual plastic, around the outside of that carbon fiber or whatever fiber was in the core. And I love where their head's at with this, but it just in principle and practice, it just doesn't work, or at least it empirically doesn't seem to work the way that they intended for it to work. And I have some theories about why that might be the case. Look, I'm not an expert, and I haven't done the actual research to verify this theory, but I believe that the reason that this stuff generally doesn't outperform just regular filament with carbon fiber in it is because the core, let's take a little step back. The filament itself comes off the spool in most cases as a filament that is 1.75 millimeters in diameter if you look at the cross section. Now that filament goes into your extruder and then melts in your hot end and then comes out of your nozzle, and most nozzles are quite small. They usually are somewhere around 0.4 millimeters. Some are 0.6 millimeters. Some are even as big as 0.8 millimeters. But either way, you're taking that 1.75 millimeter filament and you're reducing its size all the way down to something like 0.4 millimeters. Now, the savvy among you would say you probably shouldn't print fibrous materials with a 0.4 nozzle. That's true. So let's say 0.6. It's still a lot of reduction that you're going from that 1.75 to 0.6 millimeters. Now, the assumption that these manufacturers are making is that the outer sheath of that 3D printing material, whatever it might be, is going to draw at the same ratio and rate as the core of fibrous materials, and I don't see any reason to think that that would be the case. What my expectations would be is that as the material first starts to come out of the nozzle, it will primarily be just the core material, just the fibrous material. Because the softer part, the part that's the plastic on the outside, that part will soften first and move kind of out of the way so that the harder part, which is the center of the filament, can come through. And so what you'll end up with is a very thick portion of the filament that's being laid down that is the core material with a very tiny skin around the outside of it that's the actual plastic, right? Now, that's already going to be weak in every direction. It's going to be weak tensily, it's going to be weak on layer adhesion. That's not going to be a very strong material. But as soon as that first blob of that fibrous material comes out, the next thing that's going to follow it is a big chunk of no core material or very little core material that's just the plastic. And it's going to kind of oscillate this way, where you're going to have this kind of like a big push of just the core material and then a big blob of just the non-core material as it catches up, as the filament kind of catches up. And if you layer that on top of it itself a bunch of times, I think that what you'll probably get is weak spots and lots of them, right? Which is going to reduce your layer adhesion dramatically. It'll reduce your strength in every conceivable way. So I love the idea, but I just don't think it works. Yeah. Okay, so adding fibers to your 3D printing filaments is one way to gain dimensional stability as PET cools, right? And lots of different materials use this trick in order to get additional dimensional stability. And that's great, but it's not the only option. One other option that we have is, instead of adding fibers to act as scaffolding, we can change the molecule in such a way that it is less likely to form into crystals. And that is what glycol modifiers do to PET and PCT. Adding a glycol monomer into your PET as you're formulating it essentially adds a chain onto the end of that molecule, which makes it much less likely to form into crystals, right? This works for both PET and PCT. You can add glycol monomers this way into the chain. They then are less likely to shrink and warp. It adds a lot of dimensional stability, but it is far from perfect. Both PETG and PCTG will still warp. If you cool them in uneven ways, if you design models that are not conducive to dimensional stability, things that are flat and large on a single build plate, they're very likely to warp, and you will see warpage if you do that. But it's much, much better than just regular PET. It's almost as good as PET with, for example, carbon fibers in it. Now, PETG is generally considered to be the second most popular 3D printing material. And for good reason. It's an excellent 3D printing material. It's very easy to work with despite the warpage. It looks fantastic. It's incredibly strong. This crate is printed out of PETG. And you can see that it has this kind of like shiny finish to it. And it feels really good. Compared to PLA, I think it feels stronger, even though testing might bear that they're either the same or PLA is even stronger than PETG in a lot of cases. But I really love this material. Now, the downside to this material is that it's extremely difficult to support. So if you have to print something that's rather complicated, you must use supports in some cases, and the compromises that you'll have to make around those supports are going to be great. Now, with some other materials like PLA or even TPU, you can mix those materials with lots of other 3D printing materials and get great supports out of them that are easy to release. They hold the material well until it's time for those parts to be released, and then it just comes straight apart. With PETG, that's just not the case. Almost nothing supports PETG well, and I will do extensive testing to show which materials can be used for supporting PETG and under what circumstances. So this is a great material to use if you don't have to worry about a complicated support system. If you need a complicated support system, I don't love PETG for this. Okay, now the other thing about PETG that's pretty remarkable is that it prints really, really, really quickly. I've done some max flow tests with my Bamboo H2D, and I've been able to successfully get max volumes up past 43 cubic millimeters per second with multiple PETGs, several of them, not even high flow PETGs. And to be perfectly honest, the high flow PETGs that I've used, they don't seem to go much faster or any faster at all. As far as I could tell, these high flow materials, these PETGs and even other materials that are designed to be high flow materials, assume that the bottleneck in your printing process is your hot end's ability to change the thermal mass of the plastic that's passing through it. Now, if that is not the thing that's holding your 3D printing process back, then those high flow materials are just not going to make a difference for you. In the Bamboo H2D's case, that's not the problem, right? The hot end is plenty powerful enough to keep up with any of these materials at that temperature or at that maximum flow rate around 43 cubic millimeters per second. I think where the Bamboo H2D starts to falter is in print head movement speed. As it starts to move past a certain speed, it has a hard time keeping up and moves slightly less accurately. Anyway, at 0.8 millimeters, the flow rate of the nozzle is not the problem. Now, similarly to PETG, you can also add a glycol monomer to your PCT manufacturing process and get PCTG. Now, PCTG is generally the conventional wisdom is that PCTG is better than PETG in basically every way. Well, certainly except for price, because PETG can be as cheap as $9 a kilogram right now. I think that this is Sunlu, is selling this stuff for $9 a kilogram if you buy it in packs of 4. That's an astounding deal. That's the cheapest filament that I'm aware of, and it's very high quality. I've been extremely satisfied with it. PCTG comes in around $40 a kilogram. There is no property of PCTG that is so valuable that that price discrepancy makes any sense, right? Now, if you have a very specific use case where you're going to be using a very specific chemical solvent or something, and your 3D print must stand up to it, and you know that PCTG can resist that solvent, but PETG cannot, then use PCTG. That is obvious and crystal clear. But the other qualities of PCTG that make it better than PETG are generally counteracted by adding another wall to your 3D print. Instead of printing with 2 walls, print with 3 walls. And the additional strength that you will get from that PETG will far exceed the strength difference between PETG and PCTG. So, especially at this cost, where we have this discrepancy in cost, you'd have to use 4 times as much PETG before you were at break even. And if you were to use 4 times the material in your print for your PETG than your PCTG, it would be so much stronger than your PCTG print that it just doesn't make any sense to bother, right? Okay, and finally, if we really want dimensional stability and we want to get the most accuracy out of our PET that we possibly can, adding the glycol modifier makes a really big difference. And adding carbon fiber also makes a big difference. So what if we do both? So consider FlashForge PETG CF. This material, first of all, is stunning and beautiful. I absolutely love this stuff. I get both of the benefits of the carbon fiber and the PETG in a package that looks visually stunning and comes in really interesting colors. This is the best of all worlds. It warps the least. It is the strongest. The layer adhesion is surprisingly good. Now, I have printed the same print using this stuff, this PETG with carbon fiber and with PLA. And the conventional wisdom, or at least the test results that I've seen, is that the PLA should outperform this material in layer adhesion, in tensile strength, in hardness, right? That the one thing that this material does, or the 2 things that this material does that PLA does not do, is it stands up to a higher temperature. So if it's left in a hot car, for example, this is less likely to deform than PLA is. PLA will melt and wilt. And secondly, this is much less likely to creep, supposedly, than PLA. Meaning if you apply a force to a part that's made out of this material, it's less likely to bend over time. But the identical prints that I've done with PLA and this is probably not a great example because I've had plenty of success with these crates in both PLA and PETG. They're fine in either material. It is crystal clear to me that the PETG is stronger in every single way, including layer adhesion, including this stuff with carbon fiber in it. It's absolutely stronger in every single way. And in practice, the differences in strength between PLA and PETG, and between PETG and PETG with carbon fiber, it's nominal, right? You shouldn't be making something that someone's life is going to depend on out of this stuff unless you're absolutely over-engineering the hell out of it. And in the cases where you're making a functional print that can use either material, you're very unlikely to encounter a use case where one is obviously better than the other. But my subjective experience is this stuff is better than PLA. It's stronger and it has much better layer adhesion. Let me show you an example. For your consideration, look at this key cover that I've created for my BMW key. This is printed out of this flash forged material in the color called Marsala. It's a kind of dark red, purpley color. And it's a carbon fiber PETG. And it is incredibly robust. It feels super premium. It feels rock solid. And I would have complete confidence opening and closing this thing over and over again without worrying that it's just going to break apart on me one day. And if it does, it does, and I'll reprint it and it won't be that big of a deal. But before I printed it in this material, I printed it in PLA. This is an identical print, and the plastic itself weighs much less than the PETG with carbon fiber. And it feels chintzy. And the layer lines, the layer adhesion is much worse, especially in the parts that are near the edges, right? Now, maybe there's tweaks that I could have done to this thing to make it a little bit better, but I can tell you with confidence that if you handed anyone these two 3D prints and asked them which one felt more substantial, more premium, they would 100% of the time tell you that this one was better, that this was something that was more significant, that this is a better print. And that this feels cheap and chintzy. Yeah, and so the ease of printing with PLA is not something that, I take lightly, and I use this material a lot. But when I really have something functional that I want to be nice, unless I'm going to go with some engineering filament, which I do often, this is pretty good. This is pretty legit stuff. I'm quite happy with it. Okay, so let's go through all the different PET and derivative materials that I have in my shop, and I'll talk about which ones I recommend and why. All right, so let's go back to the stuff that we started with. This is PET. It's made by eSun. It's white. I think it's really nice material, but I dread printing with it. I have printed successfully in some cases with it, but it does work like crazy. It's just not that easy to work with. I don't recommend picking this stuff up. It's pricey, and kind of inexplicably pricey. It shouldn't be as expensive as it is. I'm guessing it's because of economies of scale, because no one buys this stuff. And for good reason. It's just too hard to work with. So don't get this stuff. Now, this Kitty-Tech PETCF that I was talking about, this stuff is legit. I would print in just this all the time if I could, but at $70 a kilogram, it's just not practical. Now, when I need something to really be able to stand up to some real beatings, I will definitely print it out of this. It is among the strongest materials that I've ever seen. There are some other materials that do compete with it that are like very high-end engineering materials, but they cost even more than this stuff does, right? And this stuff is already amazing. Depending on how lazy I am, you might be looking at B-roll right now of an RTX receiver that is jutting out sideways out of the side of my house with a satellite dish on it, a tiny satellite dish on it. And the arm holding that dish is printed out of this material, PETCF. And it stands up to weather, to sun. It takes a real beating, and it's incredibly strong. And it's been up there for a little while now. I have real confidence in this stuff. This is strong stuff. This is really good. Just pricey. It is currently 100 degrees outside, and you can see my crazy mast sticking off out of the side of the house with my RTX correction satellite dish pointed at the southern sky. Originally I thought that it might be able to see through the soffit, but it can't, so I had to make this extension arm. And this is PETCF, and man, it is really holding up. It's been up there for 6 months or so. It's seen storms and wind and everything, and it is just a tank. Unbelievable, this stuff. Can't recommend it enough. I mean, if you think about the forces going through this thing at the moment of the satellite dish, this levering effect going all the way back, you would expect this thing to fail. As a 3D print, it would have to be impossibly strong to hold that much force, and it's effortlessly doing it. So yeah, big endorsement for that material. Good stuff. Okay, next up is Bamboo's PETG that is high flow, HF PETG. This stuff is overpriced, and it does not print any faster than any other PETG that I've encountered. I've done a lot of testing on it, and I can't get it to go faster than anything else. It looks nice, it's high quality. I have all the same problems that I have with every PETG with it, and all the benefits from any PETG. But the high flow part is gimmicky, because it definitely does not seem to print any faster. Now, let's qualify that, because Bamboo's slicer settings for this PETG HF does print significantly faster. But you can use those slicer settings on any PETG. And in fact, you could tune any PETG to be faster than this. Faster than the settings that Bamboo recommends in their default settings on that slicer. So yeah, I'm not convinced by this. This is like a software thing as far as I'm concerned. It just does not have the benefit that it claims to have. I've got the exact same material. This is the PETG HF in the color cream. I think it looks nice, but whatever. Now this is Bamboo's standard PETG in white. It's also unremarkable. And in fact, I don't actually recommend this material because it's generally a little bit more expensive than its competitors, and the competitors are just so good. So, and so cheap. So it doesn't make much sense to buy this stuff. It doesn't blow me away. It doesn't have anything that's kind of unique about it. It's just fine and just a little bit too expensive.
Okay, this is Bamboo's translucent PETG, which I have in several colors: so orange, green, purple, blue. I think I have some others as well. And aesthetically, it's quite pleasing. It is definitely not transparent, but you can vaguely make out shapes behind it if you especially use just like a single wall, and ideally if you use a thinner wall, right? So it's kind of a tough thing though, because the thinner your walls are, the more layers you probably have. Well, that may or may not be true, depending on how you configure your slicer settings. So if you're smart about it, then you want to have really tall walls that are very thin or narrow. If you want your the vertically stacked orientation to be the most translucent. If you want the bottom or top to be the most translucent, then you want to have the widest possible walls with the thinnest possible, with the lowest possible height. And that can give you like a pretty good effect that may be close to translucent with like kind of, you know, rings that obscure your vision. It's pricey. It's not particularly fast printing. It otherwise performs similarly to other PETGs. I think that in the right use case, if you have something, a model that you want to print that should be almost transparent, should have that kind of aesthetic, it's not a bad choice. But yeah, I think I've got like a little bit of I don't think that I would recommend buying this unless you had the very specific use case for it. Definitely don't stock up on it the way that I did. It just doesn't make any sense. All right, so this is the Flash Forge material that I was just talking about. It's PETG with carbon fiber in it. And this is among my favorite 3D printing materials. I use this for anything that has to be, you know, strong, durable, aesthetic. But I don't use it just willy-nilly because it's really expensive. I have it in iris purple, marsala, and dusty pink, and it just looks fantastic. They did such a good job with this material, and I really do recommend having some of it in your shop. But again, not a material that you want to print with every single day. Okay, next material, D-Plea Rapid PETG. Now I think that this stuff is probably made in the same factory as the Elegoo. I've heard some rumors that that is the case, and that this is their like whatever cheap low-end filament. Now, I've had no problems with it. I think it's great. The only issue that I have with it is that it's on these damned cardboard spools. I hate cardboard spools. They drive me insane. I really wish that everyone would get on board with the bamboo refill thing. Now, I'm starting to see more and more of those, and they will quickly become the only filaments that I recommend. But this stuff is not bad. It's pretty good, and it's unbelievably cheap. And I'm talking about $11, $12 cheap per kilogram. And you can get it on sale for even less, right? So I do recommend this material, although I hate these stupid cardboard spools. They deform, and when they do, they get jammed in the AMS. It's just crap. I really wish that they would stop making them this way. Now, one thing that I have noticed about these D-Plea filaments is that sometimes they come out of the bag dirty, like they've been rolling around on the warehouse floor or something. I don't know, that strikes me as odd, but I think that this material is absolutely wonderful, and I have not had any issues with product quality other than the dirt, which is weird. Yeah, cheap and good. I recommend this stuff very highly. Next, we have PCTG. This stuff is made by 3D Best. I'm not aware of any other product 3D Best makes, but I bought a couple of their PCTGs at this point. This PCTG is clear, which is why I got it from these guys. It looks good as a clear material. It is relatively transparent, but it's way, way more expensive than clear PETG, and the qualities that you get from this stuff are just not worth it, in my opinion, for the price that you pay, as I've already discussed. And that goes for this stuff as well. This is 3D Fuels Pro PCTG. What is pro about it is a mystery, not just to me, but to anyone who's come across this material. I've used it for several things. I've used it for a mold for making soap, and it does fine for this, right? It's a very high quality, good material. I'm very happy with it. It looks nice. It's all fine. But again, it does not justify its own price. Too expensive. I had a roll of this in olive green. I really liked the color very much. The prints that I made with it came out amazing. I love it. It's good stuff. But just print with PETG, it's so much cheaper. This is $40, $50 a roll. And the last material that I want to go over is Sunlu's PETG. Which is an amazing material, and it also comes in refills that fit the bamboo spools. This spool is a reusable spool, which is awesome. You can buy 4 packs of this stuff for less than $10 a kilogram. That makes this stuff one of the best materials to print with, alongside the D-Plea, which I'm very happy with as well. This Sunlu stuff is as cheap as any filament that I've ever had, and prints much faster than any filament that I currently have in my shop, at least from the testing that I've done so far. And I've tested a lot. I've tested a lot of my filaments to see what kind of maximum volumetric flow I can get out of them before they start to fail. This stuff is the fastest, tied with this D-Plea. Yeah, I think that this is my recommendation. If you're buying PETG, buy it in refills. Buy it from a company that makes refills. Sunlu does. They also make refillable spools, which is great, and they can get this stuff for so unbelievably cheap. It prints so fast. This is my pick. So if you're going to have anything in your shop from a PETG perspective for most functional prints and you don't need it to be particularly aesthetic, this is the stuff that I say you go with. Now, you can get this in other colors too, but you pay for those other colors. Actually, let's take a second to talk about colors of 3D prints. Now, the conventional wisdom is that black is best. I don't know why that's the conventional wisdom. I don't agree with it. I think that black is not best. Black is nice because it's usually really, really cheap. Black is nice because it hides imperfections very well. Black is nice because it sometimes actually looks nice to have your prints in black. But the idea, one of the claims that I've heard is that black filament is somehow has better layer adhesion or is somehow stronger than other colors of filament. And there's been plenty of research in this by institutions and universities, and that just isn't true. It's not true, okay? Black materials, black dye, does not somehow make a 3D printing material stronger. And that also goes for white filament, which the conventional wisdom is that white filament is dyed using titanium dioxide, and that titanium dioxide somehow weakens layer adhesion for 3D prints, and that is false as well. It's just not true. As a matter of fact, research that has been done on 3D printing materials and colors has indicated that white titanium dioxide dyed filaments tend to be just slightly stronger. But in practice, the difference in strength is not something that you're ever going to encounter. Your colors don't matter. They just don't matter for quality, and they don't matter for strength. They do matter for cost, right? They do matter for cost. Black and white tend to be the cheapest. Sometimes you come across materials that are gray and they're a little bit cheaper too. Now, companies like Bamboo Lab, they just make all their stuff the same price. But on Amazon, if you go and look at stuff, you'll find that black, white, gray are often the cheapest, and that you pay a premium for other colors. Now, some tips around colors, if you can get them cheap. I prefer not to use black, and I prefer not to use white, even though I have a ton of black, and it's because it's so damn cheap. I prefer to use a color, and the reason that I prefer to use a color is twofold. The first reason is that black prints are very difficult to see using my Bamboo Labs H2D webcam, and the same is true for my X1 Carbon as well. So I can't see defects as it's being printed. It's very difficult to tell if my print is going well or if I should stop it without coming down and investigating in person. Now, using a color like blue or purple or red tends to make imperfections pop. It makes details very obvious. Glitter materials, things like PLA with sparkle in it or PLA metallic, those textures make it very easy to see the quality of my 3D print. And so I much prefer those, right? But you're going to pay a big premium for things like sparkles and glitter and all that. So it's not a great idea for just that reason. Now, white has the same problem as well, right? It's hard to see imperfections in white 3D prints, especially on a webcam, where the contrast can be high enough that all the white details are washed out. So what I like to do when I can is anytime that I have a specialty material that I'm printing with, I always buy that material in the same color. That helps me to know in the future when I'm looking back at which PLA did I just print or which PETG did I just print. This crate is this black shiny PETG. I know that it's either Sunlu's PETG or it's Deep Lee's PETG because that's the only material that I've been printing in this particular black with. Now, I have some light blue crates. Those light blue crates are all PLA Meta made by Sunlu, and we'll talk about that in another episode. But I try to be consistent
with the same colors for the same materials, so that later when I pick up a crate, I know who made this material, and if it has some sort of like failure or it behaves in a way that I didn't expect, it's very easy for me to point a finger and say, like, I know what material is not functioning the way that I expected it to, or in a way that I prefer, and so I can, or I pick something up and it's held up despite other materials seeming to crumble around it, and I know, hey, that material's really stood the test of time, right? So that's my recommendation. I use color coding to identify which material things are made out of. You don't have to do that, especially if you have a smaller selection of 3D printing materials in your shop, which I hope you do, because there's no one who needs this kind of variety. This is insane. I'm a crazy person for doing this, but if you have that kind of consistency, then you'll always be able to turn back and see exactly what material is being used and when. And ideally, if you use a color, then it's very easy to tell that you have a successful or defective print, even through a webcam, without having to come down and investigate in person. Now, that said, it seems like the trend is that black and white filaments are just cheaper, and they're going to be cheaper for a while. Things like this PETG black at less than $10 a kilogram is a steal. And yeah, you could probably get the red stuff or something for $12 or $13 a kilogram, but it's not worth it. It's not worth it. The black is just too good at this price. Okay, that's all the PETGs in my shop. The only PETGs that I'm recommending are Sunlu and Deeply, although Sunlu, really exclusively Sunlu, because of the refills and spools. And then I'm not ignoring the incredible aesthetics that you can get from different 3D printing, PETGs, PETG with carbon fiber, and so on. And I definitely don't want to ignore the incredible capabilities of Kiditech's PET with carbon fiber, which is just such a strong material that you can really use that in cases that will definitely take a severe beating. So if you need something super strong like that, then that's the way that I would go. Okay, that's it.